Hey y'all, in this video we'll see the Johnson-Lindenstrauss lemma. The Johnson-Lindenstrauss lemma and its extensions are workhorses in dimension reduction, and I actually use them all the time in my own research. So let's get started. Previously, we saw a way to embed any metric space with n points into L2 with distortion big O of log n. If we start with an arbitrary metric space, like this gnarly one here, it turns out that this big O of log n is the best we can do in terms of distortion. But what happens if we start with a nice metric space? Today, we'll focus on the case where our original n-point metric space lives in some high-dimensional L2 space. That is, we're going to start with n points in R to the d with the L2 metric, and then we're going to embed them into a much smaller dimensional space of dimension about log n. By focusing on this special case, we'll be able to get distortion much better than big O log n. We'll actually be able to get distortion 1.1, or 1.01, or 1.001, or more generally, 1 plus epsilon for any small epsilon we like. The main result we'll see today is called the Johnson-Lindenstrauss lemma. This result has tons of applications in dimension reduction and algorithms in general, and we might see some of these applications later. The lemma says the following. Given any epsilon in 0, 1, and any set x in R to the d of size n, there exists some linear map f, which maps R to the d into R to the m, where m is big O of log n divided by epsilon squared, in particular much, much less than n. And this linear map f is going to embed our set x with the L2 metric into R to the m, also with the L2 metric, with distortion at most 1 plus epsilon. Recall that this means that if we have 2 points in x, say x and y, and the distance between them, the L2 distance, is delta, then in the image we have f of x and f of y, and the distance between them is going to be delta times 1 plus or minus epsilon, up to some appropriate scaling. This is pretty cool, because it means that if we have n points in some arbitrarily big dimension d, we can embed those points in a reasonably low dimensional space without distorting the geometry too much. To prove this lemma, we're going to define the map f using some randomness, and then we're going to show that with high probability, f has the properties that we're looking for. This will show that such an f exists, which is what we want to show. Our map f is defined as follows. Let A be a random m by d matrix whose entries are independent Gaussians, each with mean 0 and variance 1 over m. Then we're going to define f of x to be equal to A times x. In pictures, A is this short fat matrix, it's m by n, and we multiply A by this big long vector x, and we're going to get a short vector f of x that lives in R to the m. Before we prove that this map does what we want, just a quick aside about some geometric intuition for what it's doing. Note that if the rows of A were orthogonal, then this multiplication by A map would just be an orthogonal projection onto the row span of A. That is, we're going to pick some random subspace, given by the row span of A, and we're just going to project our points onto that. You can check that if A is chosen with independent Gaussian entries, then the rows of A are almost orthogonal with high probability. So intuitively, what this map is doing is basically a random orthogonal projection. In fact, Johnson and Lindenstrauss originally studied random orthogonal projections. This version with the Gaussians that we saw is easier to generate and compute with, though. Okay, so back to the proof. We have this short fat matrix full of Gaussians, and we want to show that multiplying by this matrix approximately preserves Euclidean distance. What we're going to do is the following. We're going to show that for any fixed x and y in R to the d, that the L2 norm of A times x minus y, which happens to be equal to the L2 norm of f of x minus f of y, is in fact equal to the L2 norm of x minus y times 1 plus or minus epsilon. Here, when I say that something is equal to 1 plus or minus epsilon, what I mean is that it's contained in the interval 1 minus epsilon, 1 plus epsilon. I'm going to be using this shorthand throughout this mini lecture. Okay, so we're going to show that this holds with high probability. we're actually going to show that it holds with high enough probability to be able to tolerate a union bound over all of the at most n squared points x, y for x and y in our set capital X. This will establish that multiplication by A approximately preserves the distances between all of the pairs of points in our set. To simplify the calculation, we'll use the fact that the Gaussian distribution is spherically symmetric. This implies that without loss of generality, we can assume that the vector x minus y is just a scaled version of the standard basis vector e1. Here, by e1, I mean the vector that has a 1 in the first place and then a bunch of zeros. So why is this without loss of generality? Well, intuitively, suppose that the picture looks like this. Let's say that here's x and here's y. Then we can think about just sort of rotating this whole picture until it looks like this. In this picture, here's x and here's y, and what this is supposed to be drawing is that x minus y is parallel to e1. But the math in this picture is identical to the math in this picture. That is, because the Gaussians are spherically symmetric, approximate projection onto this subspace has the same probability as approximate projection onto this subspace, and so the probability that the distance between x and y is approximately preserved in this world is the same as the probability that the distance between x and y is approximately preserved in this world. So we might as well study this world, which will make our lives a little bit easier. Okay, that's not a rigorous proof, but hopefully you're more or less convinced. It's a good exercise to try to make this rigorous. Okay, so given that simplification, our new goal is the following. We have this random matrix A, and we're going to multiply it by x minus y, which we're assuming is parallel to E1. That is, x minus y has only one non-zero coordinate, the first one, and the value of that non-zero coordinate is the L2 norm of x minus y. We want to show the same thing that we wanted to show before, which is that the L2 norm of A times x minus y is approximately equal to the L2 norm of x minus y. However, in this nice new simple setting, A times x minus y is just equal to a scaled version of this first column. Let's call that first column y. That is, A times x minus y is just a vector of Gaussians, where every entry is the L2 norm of x minus y times some independent Gaussian. Therefore, this thing that we want to show is the same as wanting to show that the L2 norm of y, that first column of A, is equal to 1 plus or minus epsilon. In order to show that, we're going to make use of this Chernoff-style claim here up in the corner. If we have a bunch of independent Gaussian random variables, z1, z2, up to zm, then the probability that the sum of their squares is bigger than 1 plus epsilon times m is small, exponentially small in m. We'll prove this soon, but for now, let's assume it and finish the proof of the Johnson-Lindenstrauss lemma. Okay, so y, which was the first column of A, is a random vector with entries that are Gaussian with mean 0 and variance 1 over m. The probability that the L2 norm of y is greater than 1 plus epsilon is equal to the probability that the L2 norm of y squared is greater than 1 plus epsilon squared, which is less than or equal to the probability that it's bigger than 1 plus epsilon. This is because 1 plus epsilon squared is always bigger than 1 plus epsilon. And from the definition of the L2 norm, and scaling up both sides by m, this is just equal to the probability that the sum over I of zi squared is bigger than m times 1 plus epsilon, where each zi is a standard normal random variable. But by this convenient claim above, this is small, less than or equal to e to the minus m epsilon squared divided by 8. Cool. So now we've proved this claim. So let's bring it back to finish the proof of the Johnson-Lindenstrauss lemma. Recall that the reason that we wanted to prove this claim in the first place is that it implies that for any x and y, the probability that A times x minus y has L2 norm greater than or equal to 1 plus epsilon times the L2 norm of x minus y is also small, in this case less than or equal to e to the negative m epsilon squared over 8. But now we can just union bound over all of the possible choices of x and y in our set big X. So the probability that there exists x and y in capital X such that the above holds is at most n squared times this very small probability, e to the minus m epsilon squared over 8. And now we can use the fact that we're going to choose m to be some term that's big O of log n over epsilon squared. And that'll imply that this is at most 1 divided by something that's polynomial in n. So this only shows half of what we wanted to show for the Johnson-Lindenstrauss lemma. This shows that it's very unlikely that there exist 2 points, x and y, in our set capital X, so that their distance is magnified by too much when we apply A. We also want to show that it's very unlikely that there exist 2 points, x and y, so that their distance is shrunk when we apply A. You can check that a very similar argument will establish that as well. But if you believe that that works, then this proves the Johnson-Lindenstrauss lemma. All that's left to do is to prove this Chernoff-style bound that we used on the previous slide. Let's do that now. Remember that z1 through zm are independent standard normal random variables, and we want to bound the probability that the sum of their squares is too big. This probability is equal to the probability that e to the t times the sum of the squares is bigger than e to the t times 1 plus epsilon times m. Here we're just doing our standard Chernoff bound trick, where we exponentiate with a parameter t that we're going to choose later, and now we're going to apply Markov's inequality. So Markov's inequality implies that this is at most the product over I of the expectation of e to the t times zi squared, all divided by e to the t m times 1 plus epsilon. Here I used the fact that the zi's were independent to pull the product outside of the expectation. Now you can check, and you should check, that the expected value of e to the t times zi squared, if zi is a standard normal random variable, is equal to 1 divided by the square root of 1 minus 2t for any t less than a half. So if you believe that, then this whole thing is equal to 1 divided by 1 minus 2t to the m over 2 times 1 divided by e to the tm times 1 plus epsilon for t less than a half. Simplifying, this is equal to exp of m times 1/2 log of 1 over 1 minus 2t minus t times 1 plus epsilon. So this is a pretty nasty expression, but we can simplify it by bounding this expression, 1/2 of log of 1 divided by 1 minus 2t. So you can check that 1/2 times log 1 over 1 minus 2t is at most t plus 2t squared for any t less than, say, a third. You could check this formally, for example, by writing out the Taylor series for this expression, or you could just plot it and convince yourself. So conveniently, I have the plot right here. Here's the plot of this 1/2 log 1 over 1 minus 2t. Here's the plot of t plus 2t squared. And you can see that indeed this one is larger for any t less than a third. A third is about here. Okay, technically also t is greater than 0. Great. So plugging in that simplification, this nasty expression here is bounded by this nicer expression, x of m times 2t squared minus epsilon t. Now, at this point, we can choose t to be whatever we want, as long as it's greater than 0 and less than a third, so that that claim goes through, and less than a half, so that that claim goes through. So let's choose t to be equal to epsilon over 4. And let's assume that epsilon is sufficiently small so that both of these assumptions are satisfied. then this is just equal to x of minus m epsilon squared divided by 8, which is what we wanted to show on the previous slide. So this establishes, up to some details for you to fill in, the Johnson-Lindenstrauss lemma. That is, given any n points in Rd, with the L2 metric, we can embed that with distortion 1 plus epsilon, very, very tiny distortion, into a much, much lower dimensional space, R to the m, where m is big O of log n over epsilon squared. A map that does this, that is a randomized map so that for any set of n points, with high probability that map is going to preserve distances between these points, is called a Johnson-Lindenstrauss transform. So we just showed that taking a random matrix with all its entries IID Gaussians gives us a Johnson-Lindenstrauss transform. Before we end this video, let's take a quick look at some recent advancements in Johnson-Lindenstrauss transforms. This slide is not meant to give a lot of details, it's really just meant to spark your curiosity. Check out the lecture notes for pointers to the literature if you want to learn more about this. So here are 3 recent advancements in Johnson-Lindenstrauss transforms. The first advancement is fast Johnson-Lindenstrauss transforms. So we just saw that if we take a short fat matrix A that's filled with IID Gaussians, that is a Johnson-Lindenstrauss transform. Great. However, such a matrix is kind of unwieldy. In particular, matrix vector multiplication by such a matrix can be kind of slow. If the matrix is m times d, this is going to take time big O of m times d. It turns out that this can be sped up to something that's closer to big O of d log d, using some ideas from the fast Fourier transform. So here's one way to do it. There are actually several. Imagine making our short fat matrix not by taking IID Gaussian entries, but rather by taking random rows of the discrete Fourier transform. This random matrix itself is not going to be a good Johnson-Lindenstrauss transform. In particular, if your set capital X includes other rows of the discrete Fourier transform, it's not going to do very well. But it turns out that a simple modification will make this work. We can multiply on the right by a diagonal matrix, which just has independent sign flips on the diagonal. And it turns out that this will do the trick. This is a good Johnson-Lindenstrauss transform. This was analyzed in a paper by Kramer and Ward. Notice that if we want to do matrix vector multiplication, if we want to actually apply this map, we can do it very quickly. So if I want to multiply this by some vector x, the first thing I do is I multiply by a diagonal matrix with independent signs. That's super fast. And then I multiply by this matrix, which just includes rows of the discrete Fourier transform. To do this, I can just basically use the fast Fourier transform, and I can do this really quickly. And so that will let me get this short vector f of x much faster than I would be able to if I were multiplying by a dense Gaussian matrix. The second advancement I want to briefly mention is sparse Johnson-Lindenstrauss transforms. Here, the idea is that instead of looking at a dense matrix full of Gaussians, for example, let's look at a short fat matrix that's sparse. That is, it has a lot of zeros in it. In this case, a lot of zeros means that about an epsilon fraction of the matrix is going to be non-zero and the rest will be zeros. This is useful not only because it can speed up matrix vector multiplication, just like the fast JL transform, but it also is especially helpful if the vector that you want to multiply by is sparse, which shows up in applications sometimes. Finally, I want to mention a recent line of work that gives stronger JL transforms. So what do I mean by stronger? Well, before the guarantee that we had was like this. We had some set, capital X, of points, and our guarantee was that for any x and y in this set, the distance between x and y was approximately preserved. Instead, we might hope for a stronger guarantee, which is the following. Once again, we have our set, capital X, but now I might hope that for any little x and capital X, and any point y, some new point, not necessarily in capital X, then the distance between x and y is going to be approximately preserved. This is a much stronger guarantee, and it turns out that this is actually possible. The embedding is more complicated and actually is nonlinear. Okay, so there's definitely not enough details there for you to completely understand any of these 3 things, but it's more meant to pique your curiosity. If you're interested, go check out the references in the lecture notes. Cool, so that's it for this video on Johnson-Lindenstrauss transforms. Thanks for watching.